let's talk about circular motion. Do you remember this formula? Distance equals rate times time. Well, let's take that formula and change it up a little bit. For reasons which will become obvious in a little while, I'm going to change rate to velocity. And I'm also going to change distance to s for arc length. That lets me rewrite this formula as s equals v times t. Now, if I divide both sides of this equation by t, I get s over t equals v, or v equals s over t. So, why all the changes? Well, remember that s is an arc length. It's a linear distance, but it's curved. So I don't want to talk about it as a line, and I want to be clear about what I mean by distance. Not only that, but since I'm talking about distance around a circle, and circles have very specific things that we call r, namely the radius, it can get confusing if I leave r in a formula that deals with circles if that r stands for something other than radius. So I've changed the r here to velocity to represent the rate or the speed, but using a different variable. So this new formula, v equals s over t, or s equals vt, is really just the distance formula, where the distance that I'm traveling is around a part of a circle. Let's take a look at how this formula gets used. Let's say you have a ceiling fan with 16-inch blades. What that means is that the length of one fan blade is 16 inches. And let's say that that ceiling fan is going around 45 times a minute. It's making 45 revolutions per minute. Now let's say that you're a speck of dust right on the tip of one of those fan blades. Or maybe you're a fly, and you want to find out how fast you're going in inches per minute. In other words, you want to know the linear speed of the tips of the fan blades in inches per minute. Our formula for this is v equals s over t. V stands for velocity, which is basically speed. S stands for the arc length traveled, and t stands for time, the amount of time that's passed. We're looking for v, velocity, and we have our arc length s and our t, but they're not quite ready to plug into the formula yet. Recall that s is equal to r times theta, as long as theta is in radians. Well, in this case, r is 16. What is theta? The fact that this fan goes around 45 revolutions per minute basically means that it turns one full cycle 45 times in every single minute. So in the amount of time of 1 minute, we have 45 revolutions, each of which is a full cycle, 2 pi. So I can rewrite my s as 16 times 45 times 2 pi. That works out to be 1,440 pi. So in 1 minute, a fly or a speck of dust right on the tip of one of these fan blades will go around, will travel in an arc that covers 1,440 pi inches. So that's my s, and that goes here in the formula. 1,440 pi is my arc length, and my time is 1 minute. If I simplify the fraction, instead of over 1, I can just write the 1440 pi. And then I have per 1 minute or per minute. So the velocity of this speck of dust is 1,440 pi inches per minute. That's the exact value. Of course, this is one of those cases where a decimal might actually be more appropriate. 1,440 pi works out to be about 4,523.893 inches per minute. Although the formula for linear velocity on a circle is pretty simple and straightforward, we had to use the formula for the length of an arc of a circle in order to know what to plug into our velocity formula, into our linear velocity formula. Okay, let's go back and take a look at that distance equals rate times time formula again. This time, instead of using distance, I'm going to use theta. And instead of using rate, I'm going to use the Greek letter omega. Looks a bit like a funky W. So now I have the formula theta equals omega times t. And what omega stands for is angular velocity. So imagine that you're the speck of dust on the tip of the fan blade from the previous problem, and that your best friend is a speck of dust a little bit farther along the fan blade, and that her best friend is another speck of dust even further along the fan blade. Well, as you travel around in a circle at 45 revolutions per minute, you're not all going the same linear speed. You're going around the same number of times, but your friends closer into the center aren't traveling as fast because they're traveling around on circles with smaller radii. Where the previous formula let us determine how fast we were going in a linear motion, this one's going to help us calculate how fast the angle is changing at whatever point we are on the fan blade. Now, because I'm interested in how fast the angle is changing, it doesn't matter where I am on the fan blade. Whereas where I am on the fan blade does matter if I'm computing linear velocity. So let's start by converting the formula that we currently have, theta equals omega t, by dividing both sides by t, the way we did for our previous formula. That gives me the formula theta over t equals omega. Or, of course, we can switch the sides and write this as omega equals theta over t. And with this formula, now we can figure out how fast the angle is changing as we go around at the tip of the fan blade, or in fact, at any point along a fan blade. So, to find the angular velocity or the angular speed, we need to know theta and t. I can write my formula omega equals theta over t and just replace theta and t. Again, here we have that the amount of time that passes is 1 minute. So t equals 1 minute. But what is theta? Theta is the size of the angle that we cover in a minute. Well, we know that the rate that the fan blade is spinning is 45 revolutions per minute, and 1 revolution is 2 pi radians. So we're going to have 90 pi radians per minute. That's our angular velocity. Notice that the label we used here is radians per minute, whereas the linear speed, the linear velocity, gave us a unit of inches per minute. That should make sense because omega represents angular speed and angles are measured in radians. V represents linear speed and lines or arc lengths are measured in things like inches or maybe sometimes feet or miles. Also remember that at each point along the way in this problem, in both parts of this problem, the part where we determined the linear velocity and the part where we determined the angular velocity, whenever we had to use theta, we had to use it in radians. That wasn't too hard because we kept going around the circle in full cycles or full revolutions. So all we had to do was remember that one full revolution in radians is 2 pi. Okay, let's set this problem aside for now and we'll just do one more thing with these two formulas. In order to write these formulas in the way in which they're most frequently represented, I solved them for their velocity variable. Before I did that, I had S equals V times T for one of them, and theta equals omega times T for the other. Instead of solving for V in one formula and omega in the other, what happens if I solve both of them for T? Getting rid of V here, so I have T equals S over V, and getting rid of omega here, so I have T equals theta over omega. Then, given that these two formulas tell us different things about the same situation, the amount of time involved is the same amount of time. So let's set these two times equal to each other. In other words, T has to equal T. So therefore, S over V also has to equal theta over omega. Okay, now let's cross multiply, and I get S times omega equals V times theta. But we have another way to write S. S is equal to R theta. So if I replace S with R theta, I get this. Now I have theta on both sides, so let's see what happens if I divide by theta. I get R times omega equals V, or again, turning that around, V equals R times omega. This formula gives us the relationship between linear and angular speed. If you know the radius of a circle and you know the angular speed, you can work out the linear speed. If you know the linear speed and you know the radius, you can work out the angular speed. The situation doesn't come up very often, but it's interesting to note the relationship between the two formulas that do come up more often. That's it for this video. If you have any questions, feel free to leave them in the comments.